you all for joining us. My name is Matt Affelt. I'm the manager for Design Team 6, and I'm an electrical engineer. We are working on an electrocardiograph demonstration board for Texas Instruments.
I'm Derek Brower. I am an electrical engineer as well, and my non-technical role is the presentation prep.
I'm Jungchun Liu. My non-technical role is lab coordinator.
I am Alex Walensky. My non-technical role is the webmaster, and I'm a computer engineer.
I'm Phil Jaworski. I'm an electrical engineer, and I'm document prep. Like Matt said, we are Design Team 6. Our sponsor this semester is Pete Semick for the Texas Instruments. Our facilitator is Professor Boole here at Michigan State. I'll just give you a little outline before we get started. Background, we'll talk a little bit about what ECG actually is, its medical uses, its benefits, and why TI wants us to build this for them. We'll go over design specifications, the approaches we're going to take toward designing our board, things like power, input output devices, stuff like that. Tools and environments is a circuit board, so we are going to have to do a lot of design and simulation using software. For design solutions, we'll talk about each component in our final design and what its role is. We'll talk about how we go about getting everything fabricated and assembled. Design concerns. Concerns we have, obviously, such as like cost being under budget, time, safety, and enhancements. Things that Texas Instruments hasn't necessarily requested that we do or required, things that we want to add on to the ECG board to make it the best possible we can. So I will pass it to Derek, who will give us a little background.
All right, so I'll give us a little background on electrocardiography, the applications of it, and of course the problem that Texas Instruments has tasked us with in regards to this. So first off, I'll mention that I'm going to use ECG and EKG interchangeably. They're the same thing. They both represent electrocardiography. So if I switch the term around accidentally, it means the same thing. What is electrocardiography? Well, electrocardiography is the measurement of changes of electrical signals caused by the heart over a period of time. And what exactly are we measuring when we're measuring the changes in electrical signals, and where do they originate from? Well, the human heart at rest is made up of a bunch of muscle cells that have a negative potential or a negative vital potential. And outside the cell, there's a bunch of positive charges outside the cell membrane. When they cross the cell membrane, they cause the muscle cell to depolarize, and this is what causes the heart to contract. And then, of course, when they repolarize, that's what causes it to expand. This is what causes the heart to beat. And the depolarization of the muscle cells in the heart is what causes minute changes on voltage levels on the surface of your skin, and we can measure these changes in voltage level. And that's what an electrocardiograph machine does. So how exactly do we measure these changes? Well, there are three different types of common electrocardiograph machines. There's a 3-lead machine, a 5-lead machine, and a 12-lead machine. Just a little definition on leads so everyone knows what I'm talking about exactly. Their lead is commonly thought of as the electrical wire and the electrode that's attached to the surface of your skin. And it's not exactly the right definition. The lead is actually any pairing of electrodes that gives you a potential difference measurement that contributes to the overall image of the heart. So in a 12-lead machine I'll use as my example, there are actually 10 electrodes. There's 1 on each arm, 6 across the chest, 3 on the left side of the heart, and 3 on the right side of the heart, and then 1 on each leg. And the pairings that actually contribute to the electrical activity of the heart are the ones on the arms pair to measure a potential difference, the outermost ones on the left and right side of the heart pair, the middle ones, and the innermost ones. These 4 pairings all provide potential differences that are measured, and they map out electrical activity of the heart that we use to display things such as heart rate, regularity of heartbeat, and a few other things I'll mention later. Those are 4 of the leads, those 4 pairings. There's 8 other leads. The 4 electrodes on the right side of the heart pair with the right leg, and then the 4 electrodes on the left side of the heart pair with the left leg lead, or electrode, sorry. These 8 leads are used to reduce noise and feedback to make a clearer image of the electrical activity produced by the heart. And like I was mentioning earlier, we can measure the heart rate, the regularity of the heartbeat. We can actually map out and determine size and position of chambers within the heart. And we can use these, of course, to determine things like irregular heartbeat, effects of drugs on a patient, the effects of medical devices such as pacemakers on a patient, all of these things determine health of a patient. The other applications of this, of course, are for animals, research purposes, and research on animal heart purposes, of course, as well. So with that description, many of you are probably wondering, well, if EKG or ECG boards have been around they have to have been around for so long, they're used widely in medicine, the medical field, why are we making another one? Well, Texas Instruments has an outdated demonstration board. It's really archaic, it's been there longer than our sponsor has. The routing's really archaic by today's standards, he told us. And the chips they use are outdated chipset. And they have actually experienced in the last few years an increase in client interest. They come to TI, come and get the expertise from their engineers, and they ask them a lot of different things, but TI doesn't have necessarily anything to show to them, but they can answer their questions, and the clients think that it's in their best interest to go and design their own board and save money that way. So Texas Instruments is not necessarily having their chips being used or their design solutions being used. So our job is to create a new board that uses current chips and current design methods that is on par, of course, with Texas Instruments engineers and what they, their level of standard, and something that they can use to display to their customers and their clients when they're talking about ECG technology and drive interest in their own chips and their own designs. So with that, I'll pass it up to Alex to talk about design specifications.
Great. As you said, I'm Alex, and I'm going to talk about some of the design specifications for our project. The first one that's going to be up is the ECG's analog front-end system, and with the driven right leg, or DRL. And as everyone in here knows, and most people know, that when you're bringing an input, it's not necessarily exactly what you want to be using. It's got interference, has things messing with it. So what you need to do is you need to make a way to get rid of that interference. So what we're using for our project is a driven right leg type of circuit, which is kind of shown down here. And it's got a brief outline of a person there. You can see that they have the electrodes on the right and the left arms. And they also have one that's on their right leg. This is the 3 lead that Derek was talking about earlier. And you have basic inputs coming through into your amplifier, which is the INA333. And those are both coming from your arms. And then the leg one itself is actually amplified before using it as an input. And then the entire output is used to reduce small or common mode interference. And the reason it's made for common mode interference, because that's interference that's coming from the system itself. In this case, the system itself is the patient or the person being hooked up to this machine. And those are very small, possibly the millivolts that we're measuring. So we're using this type as our actual way to get rid of that interference. As far as power goes, we're going to be using a 9-volt battery, using a buck converter with a low dropout. And the reason that we're using the buck converter is because it's a step-down DC to DC converter, so we can actually use the voltages we need. And then the INA333 amplifiers are what we're using in this right here, which is basically a combination of 3 different amplifiers using high input impedance. And all of these combined together should make a streamlined design so that our actual inputs are what we want to be using for our circuit. Some more design specifications would be the inputs and outputs of our actual system. The input itself, when we're starting out our design, is going to be simulated using an ECG simulator. And the simulator that we chose to use is CardioSim 2, because we can get that provided to us from our sponsor at TI. This is a picture of what it's going to look like on this side. And the idea behind CardioSim 2 is that it can generate 11 different types of arrhythmias. This includes like your standard resting heart rate, but it also includes anything from a irregular or premature atrial contractions, which are different problems that the heart can actually incur and that would be actually tested in a real life scenario. Now, the idea behind the project is to eventually move away from using that and using electrodes or actual test pads as our AFVs, but that will be talked about more when we get to our enhancements for our project. And as far as the output goes, we're going to be using the Stellaris microcontroller module as our output source, and that's going to be gone in depth as well later. But the general idea you need to know about is that it's being used to do the back end work for our circuit, and that it's going to be outputted to a LCD screen so that the person can actually see your output. You can actually see the wave that's being produced, so you can measure your heart rate beats per minute. And now we'll be passing it along to Matt to talk about some more of our project designs.
So along with some of those other things that Alex was talking about, like having to use the INA333 and those kind of specifications, we also have some other design constraints. We have to be able to design this PCB board, and you can't do that by hand. And so the software that was recommended to us by our sponsor, Pete7, was PCB Artist. It's a free software that we can just download, and the best advantage of it is when we're done, it's easy to ship it off for fabrication, which I'll talk about later. The other tool that we'll have to be using is Tina TI. Tina TI is a SPICE-based simulation software that Texas Instruments has created. It's another piece of free software. This software includes all of TI's library and all of their chips that they've designed and their electrical characteristics. This means that like when we are doing our SPICE simulation, instead of just having resistors and capacitors and defining those types of constraints, we have all of Texas Instruments' library. So when we have the INA333, the simulation software knows exactly how it's going to react to all of these different inputs because TI has already created this library for us. This will save us a lot of time and a lot of money because this means that we can set up our circuit and test it, and we know that it's going to be exactly what it's going to be like when we build it. So that way we won't have to send off for a design, get it back, test it in the lab, find out it doesn't work, and go back and do it all over again. We can make sure our design is flawless before we send it out for fabrication the first time. Now back to fabrication. The ECE shop does do printed circuit boards. However, there are some severe limitations. They only do 2-layer boards, and they don't do plated through holes. And what that means is when you drill a hole, usually you want to connect the top layer and bottom layer. And what they don't do that. So we would have to take a wire to put it through and solder it together to connect the top layer and bottom layer. Also, as we get deeper into the project, our circuit's going to get more and more complex. And this means that we may need more than just 2 layers to do our wiring. And so we'll have 4 layers. And that's one of the things Advanced Circuits offers that the ECE shop doesn't. And that's why we'll be using Advanced Circuits to fabricate our boards. So like I said before, PCB Artist allows us to create the circuit and then just click a button and it'll send it off for shipping. And so here you can see some samples that we've already created for our sponsor P7. These are also demonstration boards that he wanted, but they're much more simple, and he gave us a schematic so we could practice and get this process down. So as you can see up top is the actual schematic like you would see in a circuits class with resistors, the op amps, etc. And then once you have that, simulate it in TI, and we can see what happens. These two are stability circuits for demonstration. As you can see, these black dots are switches, and when the switch is open, it'll oscillate because non-ideal op amps, which are the only thing we have in the real world, can't drive capacitive loads very well. And the same thing's true with a high input or high impedance feedback. It doesn't work very well. So these two samples are just some things that we'll be putting together to practice. And then once you have this circuit, you have to design the circuit in a PCB format. Now these two boards are dramatically enlarged. This board is 2 inches by 1.5 inches. For reference, your thumb is about an inch wide. And this board on the other side is 1.5 inches by 1.25 inches. That means that together, the boards are this big, and then we have all these components that we have to solder without breaking any of these wires or traces. So that leaves us with assembly. How do we put these boards together? So we had a couple options. With Advanced Circuits, we could pay them more, and they would be willing to put the boards together and ship them back completely working. The problem is it costs a lot of money, and it also takes a lot of time. The other option was that Pete Semick has the facility down in Texas Instruments in Dallas to do these as well. The problem, of course, again, is it takes time to ship it. So our last option is to do it in-house. The ECE shop offers some soldering assistance, but most of this will just be done by hand by us. We think that this will give us the best turnaround, even though it'll take longer for us to do it than a trained technician. It'll be worth it not to have to ship it around. So finally, to actually design the ECG board, we had 3 possibilities. We could work off Texas Instruments' old design, which was really outdated. It would take a lot of work to update it with new chips, new technology, new routing procedures, etc. We could base it off commercial models, which exist in places like hospitals and things like that are currently using these technologies. But again, we have to keep in mind this is a demonstration board for TI. They want to be able to take this to their customer and say, here's something we did with our chips, with our products, buy our stuff. And so basing it off a commercial product, which is going to cost them money and it's already patented or designed by someone else, isn't really a viable solution as well. So we'll have to be designing this circuit from scratch so that TI can show it off to all their customers using their products and their techniques. There's a 50-page document that TI publishes on how they like to produce PCBs. And so that'll be some of our design constraints as well to make sure that we have a very efficient and low-noise printed circuit board. Next, I'll be passing it off to Zheng Sheng to talk about some more of the cost or enhancements.
Okay, I'm Zheng Sheng, and after the design the ECG boards, we could have some enhancements. So on the input sides, we could have electrodes and or PCB pads on the left pictures on there. For using the electrodes, it's done without entering the body and using X-ray. But the downside is the area where the electrodes actually attaches, it could have a rash and irritations. So we could use PCB pads, which is you place your thumbs and fingers on the boards and detects the electrical activities. And on the output side, we integrate the Stellarius evaluation kits to detect input signal from the AFE. This evaluation kit enables the rapid evaluations and prototyping of the Stellarius microchip designs. And the target applications are fire security, medical instrumentations, factory automations, and test and measurement equipment. And for our design concerns, we will use it as a testing equipment. This evaluation kit is a compact and versatile platform for this microcontroller. It emphasizes the features including the USB 2.0 4-speed controller and analog to digital converters on this side, on here, and serial interface. There are 4 ADC channels, top here, up here into 2 differential channels to carry out the oscilloscope applications. So we can display the signals, the input signals of AFE on these LCD displays. And the actual dimension is about 2.5 times 4.7 inches, so which is a good choice for the detecting the signals. So after the enhancements, safety and fabrications are the project design concerns. Because the clients or users are directly attached to the ECG boards, we need to have a proper protection circuitry, such as power supply isolations and current limiting resistors. Also, there are a large amount of component goes into place on the ECG boards. They could possibly emitting the electrical magnetic wave. And if a human body are exposing EM wave in long term, it could possibly damage the human body. So we could use a shell drive or casing in the input of an AFE. And as mentioned earlier, the advanced circuits would be the main source of fabricating PCB boards. And it costs $33 for 2 layers and $66 for 4 layers. And throughout the designs, we need 4 2 layers and 4 4 layers, and it costs about $400. And TI provides the chips such as the INA333 and also the ECG simulators, which is CardioSync. And it costs about less than $50 for the miscellaneous parts. So this total adds up to around $450, which is under our budget. And I'll pass it to Phil to run it out.
Once again, Phil Jaworski. Just to recap everything, we talked about background. We talked about ECG, its medical uses, its purpose. It takes measurements from the heart. It's important. TI's problem is that their board right now is outdated, and they want a new one with new components, one that works smoothly. Design specifications, we talked about our analog front end, which is our analog to digital converter. So how we can take our input signals and eventually read it on our scope, and how we're going to take the driven right leg approach to our circuit, and also use other noise cancellation techniques for optimal signal responses. Tools and environments, we are using PCB Artist for design, like we showed you, and TNTI for simulation. Both were requested from Texas Instruments, so that's what we have been using, what we will continue to use. For our design solution, we talked about the design, what's actually going in it. We're using the Texas Instruments INA333 chipset, which is what they requested. We're using this Stellarius microcontroller and scope. We're simulating with CardioSync 2 before we move on to electrodes and PCB pads. For our final product and fabrication, we talked about how we are going to get most of our products, most of our components fabricated, outsourced, sent to us, and we're going to assemble most of it by hand. Enhancements, we talked about how we're going to use the PCB pads or electrodes, and how we're going to integrate everything in with our microcontroller in the end. and design concerns. Safety is a concern for us. We obviously don't want any harm to the user when they're using our product. Turnaround time, we know our turnaround time is pretty well, so we can get all our components here on time and on schedule, so we can have our final product ready for December. And parts, we were under budget, so in case anything does go wrong, we do have a little bit of room to get a new component if something breaks or replace it, get everything working. So that's our project. Any questions?
All right, we have time for one more question, so. Well, I guess just more of a comment than a question. When you're doing surface mount soldering, the equipment makes all the difference. So maybe talk with the shop; they can get you some better soldering equipment than what we have in the lab to do those precise soldering tasks.
Yeah,
So.
that's certainly something we'll have to look into to make sure that, we ordered extra boards for the first demonstration one so that we have time to practice when it
Right.
comes to the main.
It's definitely doable. It's you just need steady hands and good vision. So.
Well, thank you.